Hello, everyone. Welcome here in Artificial Intelligence and Data Analytics Lab at Prince Sultan University. Welcome to this workshop. Our workshop is titled Diabetic Retinopathy Grade Classification Using Vision Transformer. Our presenter, Dr. Sarah Attaif, she is a PhD fellow, and let me give you a brief background of highlighting the achievement of Dr. Sarah. Dr. Sarah is a Google PhD fellow at INSEAD UMR Morocco. She is an NVIDIA DLI instructor, also a university ambassador. She is the lead of TFUG Calabasa. She also contributes to AI for Good project using her machine language knowledge to create a positive impact on the society and on the community. She also involved in several competitions to improve her skills. With AI Wonder Girl, she won 4 different prizes. Welcome, Dr. Sarah, and we are expecting a lot from this workshop. And the floor is yours, Dr. Sarah.
Thank you. So actually, just one clarification, not a doctor yet. Actually, I'm in my second year PhD. I'm expected to graduate on January. But yeah, apart from that, everything else.
You are there, inshallah.
It's all right. Thank you. Yeah. And just try to share my screen so I can get started. Please let me know if you can see it.
Yeah, we can see your desktop.
Okay.
Yeah.
How about the presentation?
Yes, it's very clear. Go ahead.
Okay. So thank you very much for inviting me to do this talk. And I have given a similar talk in Devoxma, which is a technical conference. But the difference was the first one was about explainable AI, but this one is mainly about the vision transformers and how you can fine tune them on your specific task. So the specific task I choose is diabetic retinopathy grade classification, as it's usually actually a very challenging task because diabetic retinopathy is grades are very difficult to distinguish between. So as you will see, actually, that's why I actually choose it, just so we can get an idea how vision transformers fine-tuned on this task, what can they do. Okay, so as already highlighted, I am a Google PhD fellow. That doesn't mean I have already got my PhD. Actually, it just means that Google kind of sponsors my PhD, and they provide a mentor and all of that. So I'm still pursuing my PhD at INSEAD. It's actually a school in Morocco. I am also NVIDIA DLI instructor and university ambassador, as well as co-founder of AI Wonder Girls, a bunch of girls gathering together, sharing advice and participating in competitions, as well as in AI, of course, for social good. So as an overview, I will be just quite quickly introducing vision transformers. I will briefly explain the difference between CNN and vision transformers. Then I will explain what diabetic retinopathy is, and then I will share the workshop with you so we can get our hands dirty. So what are vision transformers? So I'm not sure if you ever heard of the just typical transformers that first popped up in natural language processing. So usually, for example, you have a sentence, they get the sentence, they break it into specific tokens. Those tokens can be words, can be anything else, depending on the algorithm that is used. And then they feed it to what they call the transformer encoder, which try to highlight the words of interest. And then after that, they feed it to a decoder that tries to do the other way around, so that we can have kind of a bi-directional, kind of a process, so that we can see the sentence from left to right, right to left, while paying attention to the order of the sentence, or of course of the words when it pops up and where, because like usually that's important in speech, so that we know the logic of the sentence. So usually in images we don't really need kind of to really truly know the logic, of the order, especially for example in this kind of case when, for example, for diabetic retinopathy, you might have several symptoms popping up in several places in the fundus. The fundus is the modality used to diagnose this disease. We will see a bunch of that later. So usually order was not a priority normally in images. So most of the researchers, because there were lots of efforts before this vision transformer that was proposed by Dozovitsky, so there were lots of efforts before that tried to replicate the same approach as what was done in NLP. That means, so instead of words, we would have, for example, pixels, and of course there were lots of strategies, but none of them worked. The only approach that worked is this one. So what happens exactly in this approach, or the architecture proposed by Dostoevsky? So what he did is that he says we should take an image like this one, for example, this building, as you can see it. So we will break it into patches. If you want to say these will be our tokens, so as you can see, it's not a pixel. It's a wall area. You can call it a window that will be broken into patches, which means several areas until, of course, we englobe the whole image. So, for example, usually if we're using an image size of 224, we would prefer to break it into patches of 4 by 4. That means we will be having 56 patches of 4 by 4 dimension. So after that, what they do is that they add a positional embedding. So you can think of that as a vector that has a bunch of numbers that they're usually generated kind of randomly, of course, in a logical way, where each one will be following the other, and then stuck to the linear projection of these small patches. So exactly what do we do in simple words? So you have this patch. Normally a patch will be a 4 by 4, right? So it's a matrix by 4 by 4. You would flatten it. That means you would have a 4 multiplied by 4. Then that would mean the dimension will be 4 multiplied by 4 this time, and then actually a matrix, so it will be like a vector. Then that vector, they stack a positional embedding that is generated kind of randomly, but in a logical kind of way, where each one will be following the other. And of course, you have this, so this is the patch, for example, the patch, the linear projection of the patch, and then the positional embedding stuck to it. So we can keep in mind the order at which each image popped up, right? In the actual big image or patch. And then what they do is, so for example, usually in NLP, so we have several tasks. There is machine translation, there is, there's classification, there is recognition of entities, and so there are lots of tasks. In image classification, usually in image, in computer vision, we do have several tasks too. All the original vision transformer that was proposed does not handle all of them, but the authors still saw it was a very important thing to add the class embedding token, which means just that we will be performing classification. So this thing is very similar to how the people in NLP did it. And then we have what we call a transformer encoder part of the network. So practically, what is interesting in this transformer encoder, what it does is just it takes the embedded patches, it normalizes the vector that we have, it throws it to multi-head attention. So this is the actual interesting thing in the architecture, I mean, in the transformer encoder. So what do we do in multi-head attention? So like the most important parts that are important. So the attention usually, like normally, we have a vector, we'll try to kind of deconstruct it to have three matrices. V, what they call value. There is the K, what they call key, and then there's the Q, that is actually what they call the query. So after deconstructing this vector into these three matrices, we will be multiplying each one of them by a weight matrix, so that our model can learn. But in simple ways, if you have ever, came across how feature maps usually, like how we actually interpret feature maps and how we interpret, for example, if you're using GradCam or anything else. So practically what you do is just that you look at where the gradient has the highest value, right? So if as a certain area the gradient has a higher value than for other pixels, then you say that the model, give more attention to this area than the others. So practically, that's what attention is. Trying to figure out where the model has the highest gradient. Multiply them together. Of course, like for example, here they transform it into linear because like in the end, what we need to output is going to be linear. So after they actually transform it, they perform a scale dot product attention. Another way to say we will be performing matrix multiplication, that in an optimized way. And then, because as I told you, we usually, like with the multi-head, we look at attention from different views, which means we will be having a stacked, number of matrices that or vectors that will need to be, kind of averaged or something. We need to concatenate them. So what they do is that they use simple concatenation, and then they will transform it into a linear dimension. So practically, this linear thing is just so that we can redimension the vector or the matrix into the dimension that we want. Because, like, if I understood correctly, the output, like, we're performing mathematical functions and, we're performing multiplication with matrices and vectors. So you need specific dimensions. If you do not respect those dimensions, the dot product is not going to have. So that's why they are used. So we can get them into the specific shape. So after we have performed this multi-head attention, what we do is that we actually we add the embedded patches like what we had before. We actually even normalize or go into the transformer encoder is added to the multi-head attention. You can think of it like how residual blocks usually work, so kind of like a reminder of what was there before. Then we normalize that input. We go through the MLP, which is just, a bunch of dense layers. But the difference is that, if I understood correctly, that like usually in MLP, what we do, we use ReLU as activation function, right? So that's what mostly practitioners use. But for transformers, they found out it was better to use gel. So that's what they do. So in this MLP, the only difference is that you're using gel, but otherwise it's, if you're using, for example, TensorFlow, it's going to be a dense layer, otherwise if you're using Pytorch, it's going to be just simple linear kind of layer. And then of course we add again what we outputted from the addition of embedded patches with the multi-head attention with the output that we get from the MLP. And like this thing here, this transformer encoder module, that's, you can think of it as your convolutional layers. So you will be having lots of them, of course, depending on how much you want. You could use 3, you could use 10, and of course, if you increase the number, you will increase the complexity. But normally after that, you would just have a very simple, fully connected layer, what again they call MLP. So those layers are a set of linear layers, so you can perform the classification. Now, what's exactly the difference between CNNs and VITs? So normally, convolutional neural networks look at the whole image, right? But as we have seen for vision transformers, they look at areas in the image, as patches of the images. And each one looks like each, we can call it neuron, even though it's not neuron. We will call them neuron just to simplify things. So we will say that each neuron will look as a dirty patch. Meanwhile, for the convolutional units, like all the neurons will be, looking at the whole image, and of course trying to find the, the best way to extract the feature maps, which means the most important regions. Now, apart from that, so because of this, the convolutional units actually only look at the local, at the local information. So because they, as you perhaps know already, we have a window kind of logic. So the convolutional neural networks will actually go through the image, kind of like patches, but they will get a feature map of the whole image at instant t. Meanwhile, for the VIT models, they will actually look at the patches. So it's like they will be looking way more into detail into that patch, which means after we finish, we will be able to extract general information. It's like when you're reading several books, right? If you read several books, you will be able to, your brain will want to pick up patterns. What figures in all of these books? What is the most important message that I need to remember? These kind of things. But if you look only at one book, like the convolutional neural networks does, you will be very good at that book. So it's like you will get only one view of the aspects you are trying to learn. So that's the actual difference. That's why they say one is local, the other is global. So apart from that, well, according to the authors of vision transformers, because that is arguable according to the architecture. But yeah, so what I said is that, so CNNs focus on local information, VITs focus on global information. We got that, we understand, and we kind of agree. For CNNs, they say normally we need more training time, even if you're fine-tuning. For VITs, if you're fine-tuning, you will need less training time. But if you're training from scratch, you will still need kind of the same amount of time as CNNs. So CNNs consume lots of resources, but VITs are kind of resources friendly. CNNs are vulnerable to adversarial attacks or changes in the data, but VITs are robust against adversarial attacks. So actually there's a paper about this, about the vulnerability of CNNs and the robustness of VITs. So the only thing I can tell you is that according to the others, if you have like only vision transformer, only transformer modules in a vision transformer, then yes, the model will be robust against the attacks. If you, for example, add CNN layers into the vids, then you will be reducing the robustness. But if you increase, for example, the number of transformers, the transformer blocks in that hybrid model, which is CNN with vids, it might actually improve its robustness. So it's kind of a trade-off, actually. I mean, if you're interested in vision transformers, it's definitely to read paper. I will drop it later on. So I just want to highlight one thing, is that for vision transformers, so if you remember, we usually split the image into batches, right? So if you have a huge image, you will be having lots of patches. So this assumption of actually them taking less time to train is a bit dependent on, the size of the image and lots of parameters. That's why usually people want to introduce CNS. So if you have, for example, a huge image, you can try to reduce the things you want the vision transformers to look at by using the CNS. But then, of course, they will be created up with robustness and other parameters. So one thing also to note that is well known is that usually CNNs have their own bias. So actually that's their power. That's one of the things that helps with the local thing. But vids usually lack this kind of bias. So bias, if you understand the real concept of bias, so bias is this kind of a way that helps you differentiate one thing over the other, right? So when you introduce it to a routine model, you help it learn, because it already knows the things to look at. So for example, if you're reading a book or a research paper, the first thing that you will be looking at is an abstract. That's the bias. I mean, why should you only look at the abstract? But that's just the way we know that we can get all the information from the abstract. So that's kind of why bias is very important. So it helps guide the model into what to look at instead of leaving it checking out everything. Okay, let's look into what diabetic retinopathy is. So practically, diabetic retinopathy is actually a disease that pops up in the eyes, of course. It is caused by diabetes, which is obviously just high blood sugar that damages your actual eyes, so the retina exactly. And if we don't try to diagnose it earlier, then you may actually become blind, because we couldn't catch it while it was developing. As soon as we catch it earlier, there is a higher chance of stopping and minimizing its growth, which is the purpose, because we still, till this day, we kind of still can't obviously treat diabetic retinopathy completely, but we can minimize its effects. So globally, so in 2010, people 126 million, the 6 million people were affected by this disease, and the projection in the future in 2033, researchers expected to that we will be having 191 million person affected, but this number actually might be even higher than that. So if you have diabetes or high blood pressure in general, it's wise to check your eyes regularly, or just try to avoid sugar as much as you can. Oh, another thing apart from sugar, so they say that what do we call it again? So not just your glucose level that needs to be checked, but also, sorry, I don't remember. Yeah, sorry, I don't remember the other cause, but everything is actually related to diet, like the things you eat. Just try to eat as much healthy as you can. So for diabetic retinopathy, as I told you, it has several grades, or just the way it develops from one thing to the other. So if you can see on the left here, we have a normal eye. So according to them, there's no disease visible. So in the second image, they say that this is a mild non-proliferative diabetic retinopathy. So practically, what we want to know here as the AI people is, what are the things that our model should look at, right? So if we're talking about the second grade if we consider this as grade 0 and consider this as grade 1. So in grade 1, the things that we need to look at are localized swelling of the small blood vessels. So you can see them actually in these huge blood vessels. Usually you will see a very small bump here in the retina. So these are what they call microaneurysms. So each grade builds on the previous grade. So for the moderate in PDR, non-proliferative diabetic retinopathy, it builds on top of the mild one. So this means that we will have blood swellings or microaneurysms, like these small things, if you can see them and hear this one. So that's a microaneurysm. And on top of that, we will have what they call hard exudates. So actually, hard exudates are just these yellow spots, if you can see them. And then we might have cotton wool spots. So the cotton wool spots are just white spots. So we have the cotton wool spots, which are white spots, and then we have the hard exudates, which are actually the yellow spots. So the severe one builds on the moderate one. But usually in this kind of case, we see more damage to blood vessels, which means you might have a really huge blotch of blood circulating around the eye. And we have like intraretinal microvascular abnormalities. So you can think of it as the eye starting to change its shape. Now in the PDR, proliferative diabetic retinopathy, so we have new vessels that are actually popping up. So and you will mostly see them in this area. So if you see this yellow circular area, right? So that's where you will see new vessels being formed, like abnormal ones popping up. It's like here, abnormal blood vessels, but you will see them near this yellow one. As you can see here, we can't see them yet. We have only hemorrhages, hard exudates, and aneurysms. But yeah, proliferative diabetic retinopathy, if you don't see these vessels, it means it's not proliferative. Okay. So I just want to remind you that mostly AI is used as a tool to help do something, right? So for example, help with diagnosis, help prioritize some tasks. And most of the time, it's not applied in computer science, which may be your actual major. It's going to be applied to another domain that has nothing to do with computer science. So the first thing that you need to understand is that you need to understand what you want to do. So if for example, you're expecting your model to diagnose a patient as having, X or Y, you need to understand how X and Y pops up in the data that you have, either text, very good at this. That's why we usually have domain experts. But as much as you understand, it will be easier for you to debug the model, understand its failures, understand its success, and you will be able to know how to improve it. Like perhaps you need more layers. You need to fine-tune parameter X. You need to improve the data quality. That's why you need to understand the domain you're applying AI to. So, enough me talking, and let's see the code. So let me just go out from this and then show you the code. So, I will be giving you the link to the notebook. Here it is. Oh, well, you can either open it right now or you can just follow me. It's up to you. So what I want you to do is to download this, because this wasn't trained on Colab, but it was trained using Kaggle. And I just put it in Colab for you, but I will be sharing the GitHub link that will give you access to the slides and this code. So just download it. So go to File. So when you open this, the link, go to File, click on Download, then download the the notebook. Then go to Kaggle, and well, you can open any Kaggle notebook you want. We're just going to use it as a passer-by kind of thing. Then you just go back to Kaggle, just so we can do this. Okay, so Kaggle. Let me go back to my main page, so my profile, code. But you can either create a new one, or just go to any one you have. So for me, for example, I will open this one. And what I want you to do is to just click on File, Import Notebook, Browse Files, and then go to the, to where you downloaded the notebook. So for me, I have my notebook on here. So I'm going to load it, then import it. Okay, so now it is imported. So after you import the notebook, I want you to click on Add Data and then choose ATOS 2019 blindness detection and click on plus. So you can add the data. Because I already have it here, I'm going to add it. So this is the data set. It's actually it's a challenge, of course, but the data set is from an Indian hospital because they have lots of people being affected by by diabetic retinopathy, and they don't have enough physicians, and of course, the costs are very high, and obviously the physicians can't reach all areas in India. India is a huge country. So what one of the doctors wanted to do in a certain hospital, he wanted to kind of, will a certain way for other simple practitioners, my baby nurses, or some people that are trained to use special tools to capture the fundus. The fundus is this thing you see here. So that's called the fundus. That's what we use to diagnose the diabetic retinopathy or any kind of eye disease. So we usually take it by using the digital fundus machine, a camera, but you can take it using different, of course, using different machines. There are even some solutions that use mobile, but anyway, the most accurate one is actually the most least expensive accurate one is the digital fundus photographic tool. So some people are really trained to take these images, but of course they won't know if someone has diabetic retinopathy or not, because they're not ophthalmologists, the people diagnosing this disease or any kind of eye disease. So what he wanted to do was to build some kind of machine learning model to just, give them an idea, to tell them, for example, this is a normal eye fundus. This one has, for example, mild non-proliferative diabetic retinopathy. So, please send this patient A or X to, the hospital, the nearest hospital, so they can get checked and, to avoid having more blind people. And this is especially true for elderly. So according to research, like diabetic retinopathy pops up around, well, it depends, of course, on the person, but mostly around like from beginning from 50 years old to up. But yeah, not so. If you're 60,
Miss Sarah,
it's better you get checked. Yeah. Sorry.
we have a question. Would you please repeat how to access the file?
Yeah.
Okay, thank you.
Yes, of course. So here is the link. Okay, you can open it. Right? So you can either open with Google Collaboratory, but it's useless for us, right? Because we're going back to Colab anyway, and to Kaggle anyway. So just download it, click on download. After you download it, go to Kaggle. You can open any notebook out there that is available in Kaggle. And then after you open a notebook, just click on File and click on Import Notebook. Browse files, choose the notebook that you have just downloaded, open it, import it, then click on Add Data, search April 2019, which is our data set, click on Add. It will be loading the data inside your, we can call it repository, your dedicated repository. So the data set has images of several fundus of diabetic retinopathy in several grades. So you'll be finding the train images here, and then there are test images. So these ones, of course, don't have the grade. It's because it's for testing. It's a competition after all. And then you will have the train.csv that has the diagnosis, which is the grade, which means no DR, mild, moderate, or severe, or PDR, which is proliferative diabetic retinopathy. And that's it. Okay. So one thing to note, this implementation of the code that you will receive is obviously not mine. It's from actually a person called Raouf Moumin. He has two versions, so he actually implemented it using the Cassandra leaf disease dataset. He has two versions. He has this one on the fine-tuning of vision transformers, and he has another version if you want to try it, which is training from scratch. Definitely recommend it, because when I tried to use GradCam so I can show you the differences between the failures and successes of the model, I couldn't, well, for the life of me right now, I couldn't access the layer I need so we can perform the GradCam. Because of that, it is best to train from scratch. What it means here from training from scratch is just that you will be coding each layer of the vision transformer. That means the patches embedding, how the images actually transform from normal images to patches, and how they are fed to, how they are transformed into linear projections, how we add the positional embeddings to them. So it has like the whole workflow. And because you're coding everything, you're coding everything yourself, that means that you can access any layer at will. And of course, you can change anything you want. It's not like here, for example, so to fine-tune, what we're going to do is that we're going to take the Keras available version, this one, the Keras available version of the vision transformers. Of course, it has been pre-trained on ImageNet on several ImageNet versions, and using like different architectures. So vision transformers, as I told you before, you have transformers, and with transformers you can have 10, 5, whatever blocks, right? So that's just what it means here. So for example, you would have the vision transformer big. It means like it has lots and lots and lots of transformer blocks. For example, if they say B16, it means it has actually 16 transformer blocks, and usually the big, large, or small refers to the patch, normally to the size of the images, and by default the size of the patch, right? Remember, the huger the patch, the more problematic it will be to train the model. It means it will take more time, it needs more computing resources. And for example, here B16 means that we will be having a patch of 16 by 16. You can already imagine the number of computer instances we would need to train something like this. So that's why we are going to the Kaggle GPU, because Kaggle gives a GPU, and actually, like, you can train at 12, which means you can train for a longer time without having to worry on running out on instances, but they do give you a 30-hour limit. So if you exceed that 30-hour limit overall, then you won't have access to any more free GPU in Kaggle. You would have to pay, I think, using the GCP version. Okay, so let's just start coding. So obviously, as always, we import the libraries we need. That means pandas, numpy, TensorFlow, seeing as we'll be coding using Keras. So here, glob obviously just so we can get the images folders quickly. The warnings are so we can avoid any kind of warnings in the code. So import matplotlib, obviously for visualization of the images, and sklearn so we can get the confusion matrix, the classification report that has endpoints for, and then the other metrics like accuracy. Seaborn again is just for visualization, pretty visualization. So it's good practice to figure out what kind of TensorFlow version you're using, because sometimes the library that you're using or the code that you will be using might actually break in version X and work on version Y. So always make sure that you print it and remember, well, usually it's best practice to, after you finish, to Docker everything with the versions that you have so people can directly replicate the same code, the same libraries, everything. So typically speaking, we most of the time use image size of 224. Most of the CNN models use image size with 224. Well, it's not a very good idea to do that, especially with medical images. It is preferable to have the highest dimension you can possibly afford, because the more you shrink the medical images, the more information you are losing. It's actually true even for normal typical images, but it's more sensitive with medical. So this image size is too small, but seeing as this is just a toy kind of, we're just trying to learn and understand how to use the model. So if you truly want to improve this model's accuracy, the first thing I would suggest is to increase this size. But if you increase this size, if you don't have access to a high computing resource, that means a better GPU, better reduce the batch size, right? So I would recommend going with a 4x4 batch size. Batch size here is actually 16, but I'm talking actually about the batch, not the batch size. But the batch size may need to be reduced too. But the batch size corresponds, like, is in relation with the memory you have, and of course the GPU. So normally 16 is very low, But I guess because we are using VB32, that means the big version with 32 patches. I guess that's why they're using 60 instead of actually using the normal 32 that we use in this batch size. So obviously, these kind of things are parameters you can fine tune. The more you increase, apart from the model being affected when it comes to accuracy, the thing that really will be affected is actually your computing resources. So always make sure you adapt this according to how much GPUs you have. Like normally, typically in research, they train using 4 GPUs so that they don't run out into these kind of issues. But we mostly don't have access to these kind of things. Normal students, of course. So we will be defining the train path. You can ignore the test path if you want. You can ignore anything that's called test here because we're not using it. After all, you can use it only if you want to submit to the CACO competition, so you can compare. But the most important ones are the training. So we get here the training path so we can feed it to the data frame. Same, actually, we're just like trying to, remember the CSV here, we have the train. So this file here, if you open it, it has ID code and diagnosis. So, sorry. We will be trying to load it into the data frame. And we will be adding the image path. So this is not obviously the full image path. This is like the directory where the images are. But what we're doing is just we're adding the PNG so that we don't have to add it later on or worry about it. But you can add the full path. If you're not going to be using data gen flow from data frame, you can adjust whatever is here. So this is like just to make it easier for us to split the data and play around the data as much as we want. I mean, of course, access to the folders and information we need, which are the label and the images. So for data augmentation, the author of this notebook chooses to use a bunch of rotations and, like when performing the saturation, contrast, and brightness, which is just playing around the images kind of lightning aspects. So he chose to play around using the pixel kind of approach. So, and he's performing rotation as well. So I actually nullified the rotation and the flips because usually in medical images, you don't want anything that's, illogical. That means having an image upside down is very highly unlikely to happen. It's very highly unlikely that an actual doctor or physician would flip the image unless it's usually, they usually only do it with just x-rays or CTs, but they don't even do it a lot. I'm not even sure why they would flip it, but I just keep it as logical as we can. So when you're doing augmentation, even pre-processing, please keep in mind that it needs to be logical, which means something that is going to pop up in real life or happen in real life. So for example, changes in lighting, very bad conditions of an x-ray or any kind of medical modality being taken is very probable, especially if you have a very poor tool. So keeping this is a good idea. You actually might want to comment this one too. Anyhow, so we will be, obviously, we need to get the data using a generator or any kind of custom data set loader. You can code your own. Nothing stops you from that. But it's always better to use what is already available. Although there is a new way to do it in TensorFlow, I mean, more shiny way and of course more optimized. But this one is good too. Like, this is the one I usually use. I prefer this one because it provides me flexibility. So flow from data frame. I put all the information I need, which means the paths to my data, like more information, some more information, metadata information too, and obviously the label in this data frame. So usually that's why I prefer to use it, and I do recommend using it because it helps you. It helps make it easier for you when you want to do the split, when you want to split your data and you want to do like different kinds of data split, not the typical usual ones that are available, which is best friend split. Now, most of the time it is better to use either a stratified kind of approach for the split or a more smart one where you keep in mind the classes distribution of the actual ratio that will pop up in the validation, which is has to be like in real life. And for the medical field, so for example, it is advised for the training to have the same number of classes. Like for example, so here we have 5 grades, right? So I need to have the same number for no DR, mild, proliferative, severe, and moderate. Same number of images in training. But in validation, I need to keep the ratio that is the most likely to happen in real life. So for example, let's say, well, obviously the highest number will be the number of people that haven't been affected by diabetic retinopathy. We can't have the whole globe being affected by diabetic retinopathy. That's impossible. Well, at least at this age. So that means the highest ratio will be for no DR. So that's what I mean. And of course, you need to respect for the other ratios as well. For the validation. So we get the data, well, the training data, obviously. So for data gen is just like the typical things you want to be seen mostly everywhere. Obviously, for the pre-processing function and validation split, it will only happen for the train gen, for the train part, so train generation and validation generation. So let me just specify for each one. So usually in CNNs, you would have a specific pre-processing function for each, right, for each model, right? So for example, MobileNet has its own way of pre-processing the data, ResNet has its own way for pre-processing the data. And what that means usually is just normalizing the data. And this is what we're doing. We're normalizing the data and then we're scaling. So that instead of having your data go from, I don't know, like from 0 to 255, you would have data going from 0 to 1. Of course, that is depending on what you want to do. Or you can have data going from -1 to 1, depending on the architecture. So for here, they choose to use a rescaling. Obviously, we'll be having from a 0 to 1. So we'll be dividing by 255. We will sample-wise center, so we can focus on the center. We will perform standard normalization. So we can, kind of have a Gaussian distribution. Then we will have a validation split of 20%. And for the pre-processing, actually it's not pre-processing, it's just a bunch of data augmentation. Remember the one I showed you before? So we just fed that function. Obviously, these will be available for training only. Like the data augmentation is going to be in the training only. And the validation split is going to be in the training only. So because here they kind of have to specify it. So we have a train generator, validation generator. For the training, we need to specify it's a training. Validation, we have to specify it's validation. And anything else is going to be the same. So our column, the X column, the data that we're going to feed our models are the images, so each image path. What we want to predict is the grade of the diabetic retinopathy, which is called diagnosis in our data. This one. Okay, and then because we did not provide, if you remember, we did not provide the absolute path to access the images, we're providing it here. So we tell this that our images actually are this train images, which means this path, this one here. As I told you, like they did define the test, but you can ignore that. So obviously for the test, no augmentation, no validation split is going to be provided. Only the pre-processing, that means rescaling, sample-wise standard normalization is going to be normally reflected in the test, but we're not using the test set. Okay, so we're going to train using 2,930 images. We're going to validate on 732. Of course, we have 5 classes. So this is just the sample after the data augmentation. So this is like, if you see this image here, this the third one here, first row, third column, this one is completely like isn't necessary and very unlikely to be seen in real life. The doctor wouldn't flip the fundus image to see it. So if you want to avoid something like that thing, please remove this transpose thing. So as you can see, this is like the data after it has been augmented, pre-processed, and centralized. All right. Now let's get to the vision transformer. So as I told you, what they're using here is the VIT-Keras implementation, this one. So we will be using this one. I would like to remind you that this is not the original implementation. I mean the official implementation. If we want the official implementation, let's check it out. Google Vision Transformers GitHub. Now, the kind of annoying thing about this official implementation is that it's implemented using JAX. And because what we want to work using is actually Keras, so we have to deal with the unofficial one. And when you're using something that is, unofficial, it means it's not optimized, has lots of, it may have lots of issues. That's why, for example, we can't exactly access specific layers. For example, if we want to change them, if you want to do something like this, you would have to personalize everything. Even this, like, you might have to change the actual implementation to make it more flexible for you to play around. But we're not interested to change anything, right? We're just interested to fine-tune this already pre-trained model for our specific task, which is diabetic retinopathy grade classification. So it's very simple to do this. So you just import the actual library after you have installed it locally. Import it, and then you import what you want. So the architecture you want. So here they are using VIT with a batch of 32. Here again, we're not talking about the batch size 32. No, we're talking about the actual batches. Remember? So, and the B is about the architecture. Is it big, large, or small? Like I told you. So this is the official implementation. Let me just go back to the unofficial one. So they usually have several implementations that they have pre-trained. So as you can see, they have the vision transformer big with 16 as batch size. They have the large one with 32 as the batch size. So you can check all of them out. And you can of course play around all of them if you want. Just to see which one works out better. So to my understanding from the several papers I have read so far about vision transformers, most people prefer to use the vision transformers big 16 version. Although the 32 version is also used, but mostly the 16 one is preferred, and mostly everyone likes to use for the image size this 384. Now, of course, for medical images. Those are mostly the papers I read anyway. So, now just as a start, we still haven't trained anything, just to let you know. So they're just trying to visualize the attention maps, right? So as you can see, they call the visualize.attention map on the model, which is bit model, and they, of course, on a certain image. We still haven't trained anything. So as you can see from the ImageNet weights, the model, according to the model, the most important aspects to look out for are the signs. Well, if you understood anything from what I was talking when I was explaining how you can, what are the things that you need to look out for to know what grade it is of diabetic retinopathy, you would know that the things to look at are this area. Remember that circular, I think it's called the ocular vein. So the circular yellow thing, that's one of the things to look at. You need to look at the blood vessels. You need to look at, most of the time, the center, near the macula. This thing that is usually in kind of gray. So it's not going to be exactly the size. Mostly it's going to be the center. But yeah, the model hasn't been trained yet, so we can judge it. All right, so let's define the model. So practically, if you remember correctly, in the slides we said, so we will be having the actual, we have the image, it's getting split into patches. The patches are going to be linearly projected. It is flattened, and then we will add positional embedding. After that, we will feed it to the transformer encoder section, right? And after that, we have what we call the NLP, well, the classification kind of network or hack. So this is the model. This is the vision transformer model, our backbone, if you want to call it that. And this thing here is our classification part. So we flatten. So after the images are actually, usually the images are flattened anyway. I am not sure why they like to reflatten them, but if you don't want to reflatten them, you can definitely remove this one, because as you can see, the shape is already 768. But yeah, then they feed them. So the author of this notebook chooses to use batch normalization. If you don't want to use it, you can definitely discard it. And then they're using dense layer with activation using the Gelu, if you remember. For transformers, they prefer to use Gelu instead of Relu. It was, of course, they gave this advice after trying for several experiments. They found that it works better. And then, again, there is another batch normalization layer. And then, of course, this is the last output layer, in which we will be using softmax because we have a multi-class classification problem. And the number of classes that we have, which is the number of grades, which is 5. So we go from 0 to 4. 0 is no DR. 1 is mild. 2 is moderate. 3 is severe. And then 4 is proliferative, right? And you give a name to the sequential kind of way you define the model. This is if you want to access, for example, this classification had, they will be calling it vision transform, even though I think it's better if you call it classification part or something, but just for it to make sense for you. So this is the kind of architecture of the model we're using. So we have the original VIT, big, 32 patches network. We have the flattening layer, the batch normalization, dense layer, and another dense layer. Well, if it was me, I would definitely not use this batch normalization. I would use dropouts instead. But yeah, everyone has their own way of doing things. Okay, so this model B, you can definitely discard it. I was actually trying to. So I defined this, I was trying to figure out a solution on how I can access the layer normalization, this part of the VIT model that is usually found in the VIT model, the original architecture, so I can perform the GradCam, which means the feature maps visualization. But it wasn't successful. I'm going to try to figure it. I mean, if I figure it out, I will send you the updated code. But right now, my advice is to just use either you use the official implementation by Google using JAX, or you actually just use the train from scratch version of, this author's version, train from scratch version of this notebook. You won't do much changes, you will just update the data. And of course, you can add the GradCam part. It's in this notebook. You can copy paste it, and normally everything should work perfectly fine after that. Anyway, so one of the parameters we usually pay attention to is the learning rate, right? So learning rate advises to start from 0, 1, and then go to 0, 3, and all of that. But usually, most everyone starts with 10 power minus 3. And if it's a deep model, especially if it's a very huge architecture, then it's advised to start with 10 power minus 4, which is 0 to 0.0004. Sorry, 0.001. If you want the 4 or 3, you can just change this one. So one thing to note is that here they're using rectified atom. So usually what I see people doing is using atom W, but here this other is using rectified atom. So practically we're not using atom, that is for sure, because according to them there is an issue in the original atom with how it upgrades the gradient. So you can either use the atom W or this rectified atom. So according to the authors, this rectified atom, of course according to the authors of the method, they say that this rectified atom gives either a better accuracy than the original atom, or actually at least a similar one, if it's not a better one. And apart from that, they say it has the model trained faster, which means that the model will converge faster. But arguably, the author of image search, so he thinks it's not true in all cases. So you might want to check this one. I mean, if you're curious about this, you might check his article. Is rectified atom actually better than atom? I haven't checked it yet because I have never actually heard of rectified atom until this notebook. Like when I use vision transformers, I usually use atom W, which you can get from the TFA dot. I'm just trying to find that import for you, but we might not find it, but let me just see. Oh, okay. Yeah, this TensorFlow add-ons. So the TFA has its own implementation of add-on, so you can use that one. It's called AddonW. And then, of course, we set the learning rate to the optimizer. We need to compile the model before doing anything, which means feeding in the optimizer we're going to use to optimize the learning of the model. The loss, obviously, we're performing multi-class classification, so we'll be using categorical prosentropy, and then they are using label smoothing. So it seems that label smoothing works out pretty well with transformers, and like I have seen this in several transformer architectures. They all use label smoothing, all recommended instead of the hard label. So label smoothing is just they perform harding the one-hot encoding, which is mean 01 thing, transforming a certain label into the 01 sequence, where one usually is where is actually like refers to when the class is activated, which means class is present in that sequence. And then they add the distribution of the labels to the one-hot encoding. It seems actually according to them, it seems to improve the results instead of what they call the hard label, which is just the normal label, one-hot encoded. So, well, the step size, you can define it, you can ignore it, but in vision transformers, most architectures, they do define it, and I am not sure like it's because it has them or not, but you can skip it and just add more effects instead of setting the step size if you don't want to have a headache with that. So reducing learning rates, very much well advised. And what it does is just that usually it's called like reduced learning rates on plateau, which means if after the model has learned for a certain number of epochs, which is actually you define, so that's what we call patience. So for example, if after 2 epochs the model doesn't improve, so here they are monitoring the validation accuracy. So if the validation accuracy does not improve after 2 epochs, then please reduce the learning rate, right? So we started with 10 power minus 4. We will go down until we reach 10 minus 6, but of course we update one at a time, not all of it in the first. So if after updating to the next, let's just say, for example, 10 minus 5, and after 2 epochs the model doesn't converge, then we will reduce some more until we reach the 10 power minus 6. So in here, the order of these notebooks actually monitors the val accuracy, right? So in my work, I usually do not monitor the validation accuracy. I prefer to monitor the loss, because what we want is to decrease the loss. If the loss is decreasing, it means that the model is learning well. But the accuracy is tricky matter, because sometimes it can go up, it can go down, and it might not really reflect the real performance of the model. But everyone has their own ways, right? So you can choose whichever way works for you. So we're using early stop-in. It means if, well, here, again, patience, so we have 5. It means if after 5 epochs the model does not converge, which means the validation accuracy here does not improve, then we will stop training the model. No matter how many number of epochs you set, we will stop training the model. And this is good practice. It saves you time, computational power, etc. So the checkpoint is just like, let's say for example, something happened, the GPU disconnected, your Wi-Fi disconnected, not working. You at least have a version to restart from. And of course, you can use it to visualize the feature maps of your model later on. So obviously the callback is just all these shiny new things that we just defined. We will be passing it to the model. That's it. So the model will start training, right? As you can see, the validation accuracy here, well, sometimes improves, sometimes is drastically bad, but the actual loss is going down, which is a good sign. That's why I told you to, with all due respect, ditch the accuracy and monitor the loss. Obviously, even the loss sometimes can act crazy. So for example, here it was 1.22, but here this is 1.26. So yeah, your choice. So here the other actually like saved the model, and they were using save weights only true, and as usually like that is not how it works, it seems, with the save. That's why I actually like commented it, but only after it had run. So that's why it's giving an error. You can run it now, it's safe. So normally I was thinking of showing you guys how you could debug your model using GradCam, which means feature maps, highlighting the most important regions that the model think was important, but this was a failure for this version of the model. And if I update it with either training on the from scratch or actually, like figuring out a way to access the layer I need from this pre-trained version, then I will just, update the notebook in GitHub and you can access it. Okay, so let me just show you the confusion matrix. Yes, let me see. Oh, okay. Sorry, let me go back to where I was. So this is a confusion matrix with the classification report that the author has had in the code. So as you can see, so I actually like plotted another one because I don't like these things like this. It is very confusing. So I will show you like the version I'm using usually. But right now, the most important thing to note is that if you check out for the classes that have the less number of images, it is logical and normal that the prediction power, which means precision, either with call or F1 score, will actually be lower than the other classes, right? That's logical. So for images that have the highest number, for the class or grade that has the highest number of images, as you can see, we have a very good metrics. So we have 95, of course, on the validation set, 97%, 96% for F1 score. Normally this is what we need to pay attention to for, as we have class imbalance, instead of course of the accuracy. But precision and recall are extremely important as well, especially for the medical field. Usually they prefer to have a high recall. If you have a high recall, it means that your model is doing well. But as you can see for the grade number 3 and grade number 1, it's very difficult for the model to have, good results, which is normal. We have less number of images in these classes. That's why I told you it's wise to follow the guidelines where in the training you have the same number of images for each grade, each class, and then in validation you have something that mirrors reality. This way the model does not favor one class over the other because it has more examples. But like in this, they didn't follow this approach. I mean, this code, of course, because they were training on another problem, which is Cassandra leaves. But I think it's best practice to follow it everywhere, but in the medical field, mostly they do take it seriously. So, yeah, it's always good to either oversample your data so that you can have the same number of images for each class, or actually, I mean, in training, obviously, in validation, make sure that you mirror what happens in real life, in the real world. Or, of course, if you don't have a way to add more data, what I would suggest and what I usually might do is that I would target classes that have the least numbers. So, for example, grade 1, 3, and 4. And then perform data augmentation only on these classes. So I can have kind of the same number, or open sample using the data augmentation. Because obviously, especially with vision transformers, I mean, I'm talking about this architecture, because there are other vision transformers that can train well using less data, like swim transformer, a data efficient transformer, which is called DATE from Facebook. And then I think there were some other new architecture that have been introduced. Like I think there was Dino, and then other people are using hybrid kind of transformers. That means introducing a CNN component into the vision transformer. So these usually are more data friendly. That means that you can use less data. Of course, don't use less than 3,000 if you want your model to actually have a chance to learn anything. Well, so this is my proposed confusion matrix. As you can see, the model does pretty well. Well, obviously, in the class that has the most data, but it does confuse mild as no diabetic retinopathy and mild as actually moderate. And the highest confusion happens with moderate being confused as mild. So this is like in real life, mild being considered as moderate or as no diabetic retinopathy is kind of normal, because even doctors these days, not these days, I mean in general, they find it very difficult to tell the difference between mild and actually moderate. So because in here GradCamp failed miserably to work, I will show you another example. I will show you another example where it's another presentation where I used a hybrid version of the transformers. So what the author of this notebook did was that they used EfficientNet, which is obviously a CNN model, as the way to extract features before feeding them to the swim transformer. So swim transformer, as I told you, is one of the ways you can train vision transformers without requiring lots of data. And the way it actually extract or performs, extract, if we want to call them patches from the data, is very similar to how CNNs extract feature maps. It's very similar, but of course we still keep the same mindset of the vision transformers, which is having patches instead of actual feature maps. So the principle they are using is called window shifting algorithm for the swim transformer. Okay, so in this one actually to compare between just the CNN component and the CNN plus the transformer component, they actually keep, because the code that is used is coded from scratch, they actually keep the output from the convnets and they keep the output from the hybrid version, efficient net with swing transformer. So this model performed way better than the one I just showed you. But of course, there were some confusions between different classes. The model, if I remember correctly, was normally like the number of epochs set was 50, but while using early stopping and all the things we saw, checkpoint and reduce learning rate from plateau, it stopped training for on the epoch of 38. So, like I told you, there were some. So the model did mistakes, obviously, had lots of failures in some classes, like, for example, here, mistaken mild as no diabetic retinopathy and mild as moderate. So, for example, here, as a human, so for example, if you check out this image, what kind of anomalies can you see? So, we can see these two dots, right? So they might be a hard exudate. This might be a cotton. There is a high chance that it might be colon. And this thing here are what we call the hard exudates, right? And this one is a this one is the hard exudate, and this one is what we call microaneurysms, which means small blood swellings, right? These small, even though they're not very clear, yeah, but this is what doctors have to deal with. Even these things are not free for doctors. So that's why it's very difficult to diagnose diabetic retinopathy and overall disease, actually. So anyway, if it was me seeing this image with the knowledge I have so far, I would definitely rate this as mild, because in moderate you would see lots of hard exudates. The small yellow spots, you would have lots of them, and the blood swellings would be more prominent, which in here they're very small. So I would definitely say it's actually mild. So why the model confused this as moderate? Because it looked at the microaneurysm and the blood spots, right? But normally it should have just looked at these, at these two contours, these two small circles. And this is what the CNN looked at, just CNN, so the efficient net. It looked at this area. Meanwhile, as you can see, which is why actually the transformers are more preferable than the CNNs, like I told you, is because they focus on the global, the global image. That means that the global features, the whole thing. They don't look at exactly specific areas where something could pop up. So, as you can see, the model spotted all kind of, they thought as anomalies, which is like this one, and then this one, and then this area. So usually, like the areas that are highlighted in red means those that have the highest activation max, kind of the highest value of the gradient. And after that, we have the yellow, then we have the green, then we have the blue. So this is the gray. So if the model highlights something in red, it means that the model thought it was the predetermining factor in the actual prediction. Meanwhile, the other areas had less weight. They did have weight, but less. It's like unimportant details, but they are still details. So the model, the model had actually lots of failures, but let's see the success too, right? So actually, in this success, it was a real success. So the model did predict no diabetic retinopathy, and to make that decision, so let's not focus on the CNN, where they know that the CNN loves to look at one spot. Meanwhile, in reality, you need, like, if you're going to diagnose diabetic retinopathy, you need to look at all the spots, right? So if you check out what the hybrid CNN transformer model did, it looked at all the areas, of the fundus. So this is the fundus, and that's the right way to do it, even though it did not look at at the yellow circular thing. Yeah, although it did not look at it, it should have looked at it, but practically it is better than the CNN at least. But when it wanted to, predict if this was proliferative diabetic retinopathy, it actually looked at this blood thing. I mean, the CNN looked at the blood thing, which is a good way of doing things. But the hybrid CNN transformer looked at the heart exudates, which usually do pop up in proliferative diabetic retinopathy, but they do come from the milled one, right? These are like aspects that pop up from the milled one in the first place, and then they can pop up in the other ones. But the most critical part that should have been, the area that should have been looked at, at least by humans, if they want to figure out if this is proliferative diabetic retinopathy or not, they would look at the circular yellow thing, if you remember, and check out if there are some newly formed blood vessels that shouldn't be there. So like I told you, usually diagnosing a diabetic retinopathy is very hard thing to do anyway, even in real life and even by ophthalmologists. That's why, so Google actually tried to build a model not a model, but an application, of course using AI, that would perform this, grade classification and help the Indian hospital, if you remember, to actually, spread the diabetic retinopathy diagnosis and help not just physicians, but just normal people, or we can call them technicians, the ones that take the fundus images using the machine to help figure out if, using AI, if it's like what grade of retinopathy is it, to know if they should send the patient to certain hospital and have them check regularly. Because after you have, even if when you're diagnosed, you will still have to visit the doctor as much as you can. So they have to make sure that it hasn't developed into something way more advanced. For example, development from mild to moderate or anything like that. But they found that even specialists, human specialists, it was very difficult for them to agree on some fundus evasions being either, for example, mild or moderate, severe, or proliferative. So if obviously even the humans struggle, then the AI, because the real labels, the real grade is provided by a physician. If you feed the AI wrong data, it's going obviously to most likely give you the wrong prediction as well, right? After all, garbage in, garbage out. So if even physicians struggle, it is going to directly translate into the AI struggling. But of course, if you pick, some kind of experts that have the least number of errors, well, you will increase, obviously, the quality of your AI prediction. So if you improve the data quality, you'll be improving the AI predictions quality. But overall, I just wanted to say that the medical field especially is very challenging to build AI tools. And even when you build them, you need to make sure that they're very highly dependent on the physician. So like the end result, the end goal is always going to be the physician that makes the decision. The AI only helps, and you need to highlight all the failure cases, all the success cases, the cohort that your model has been trained on, all the information that you can provide about your model, the data, anything surrounding the solution you are providing, the more you are increasing the efficiency of your solution and decreasing the risk of someone being misdiagnosed, or of course a dilemma happening. But that was it for me. Thank you very much for your attention. If you have any questions, please go ahead.
Thank you, Ms. Sarah. That
I
was
hope I
very
didn't
informative.
exceed my time though.
No, it's okay. Thank you, Ms. Sarah. That was very informative, and the implementation and recommendations, and it's I think all of attendees here agree on the challenges of healthcare application, as you mentioned, and we try to come up with the ideas, as you mentioned, applying AI in this field. Thank you for this session, and if the attendees have any question, they can ask Ms. Sarah.
Yeah, please go ahead.
I would like for the attendees to fill the registration form for the certification. And thank you again, Ms. Sarah, for this interactive and very informative session. And inshallah, soon we'll tell you, Dr. Sarah. We'll invite you again, inshallah. Thank you all.
Thank you.
Thank you all attendees. Couldn't import. We have a question. I couldn't import the POTUS 2019 data in the chat.
Okay. Yeah, okay. So as I told you, if you want to import the data, so normally, for example, sometimes if you open a notebook, it will look like this. Just go to this place here on the upper right corner and click on Add Data. Then click on the name of the competition, which is normally APTOS 2019 blindness detection, and choose this one. Click on, so because I have it here, I can't click on this, but then you remove it and then add it back up again for you. So you click on the plus and then they add it directly to your input. So of course they will tell you here, I mean, they will send a notification telling you that your data is loading, is being uploaded, and later on you will find it here. But that's it. Usually it should work. If it does not load, it means there is a connection problem. That's mostly the case. Or otherwise, you can upload any kind of available data, open publicly available data into any kind of Kaggle notebook. Of course, using Kaggle.
Ms. Sarah, can you please repeat what should I write in the search box so I can find the data? Can you please?
APTOS 2019 blindness detection. And please choose the one with the blue logo, with the blue background logo and a name. This one. So add data, APTOS 2019, right? Blindness detection. See, this one, it's the first one. Can you see it?
Yes, it's clear.
Okay. You just click on add and then it will be added. But if you have connection issues, of course it might not, not be added.
So, you're welcome. If you have any question, another question to Ms. Sarah. So thank you again, Ms. Sarah, and we will end this session, workshop, the informative workshop. Thank you all for attending.
Thank you, everyone.
Thank you. Bye-bye.
See you.
See you again.